Hello everyone. Welcome to the TCS seminar at Jagiellonian. Today our guest is David Conlon from California Institute of Technology. David is well known for his research on Ramsey theory, external graph theory, or just external combinatorics more generally, and additive combinatorics. And today he will tell us about additive combinatorics without much addition.
Thanks. Okay, so everything I'm going to talk about is joint work with several people. So it's joint with Jacob Fox, who I work with a lot, Polly Pham, who was until recently a PhD student of Jacob's, and now a Clay Research Fellow, and Liana Yepremian, who's at Emory in Atlanta. Okay, so let me set the scene by there's an old result of so as a result from the 70s. Nowadays, if you work in this area, it looks very, very straightforward, this result, but I think at the time it was less so. So it's a result of Bulabach and Erdős, and it was proved independently by Tula. And the result is that the clique number of the binomial random graphs, and I'll say what these things are, is, let me just make it a half, is 2 plus little o1 times log base 2 of them. Okay, so this is just the clique size, so the max clique size. And this here is basically the random graph where we choose each edge independently with probability of half. So each edge has probability of half. And of course we could put p here instead of a half, but that changes the constant. Okay, so this is a classic result. It's, as I said, very easy. One direction is really very easy, and the other direction takes a little bit of work, but is very straightforward and with modern different. Okay, so the kinds of questions I'm going to be concerned with is what happens if you look at Cayley graphs instead of just general random. So a Cayley graph, given a weak gamma and a symmetric S contained within gamma. So what I mean by symmetric is that if S is in S, then its inverse is also in S. The Cayley graph K gamma S is the graph with vertex set, so it has vertex set equal to the group, and 2 edges are joined basically if they differ by an element of S. So xy is an edge if and only if x, y inverse is contained in S. And the reason you make this symmetric is because you want the same thing to be true, that yx inverse also denotes an edge, but yx inverse is the inverse of xy inverse. Okay, so this is a very, very standard definition, and you can also look at random Cayley graphs. So a random Cayley graph, so gamma of p is random Cayley graph where each set S inverse is in S with probability. So, and if p equals a half, you get the uniform random variable. So, so these things are much more constrained than the random graph. So a random graph like this, everything appears with probability of half, each edge is independent. Over here, that's not true. You're not in the case where each edge is independent because a lot of these edges are actually coupled together. So for example, if you're working over Zn, and S is just equal to, say, the set consisting of plus or minus 1, then you get basically just a cycle. So it eventually loops around at the end. So that's all that is. But if we had chosen a random thing, then all of these edges either appear together or not at all. So it's in that sense a Cayley graph. You're getting blocks of colors appearing together. Okay. All right. So here's a question. The question was asked by several people, or studied by several people, but it was certainly asked by David Conlon in the 90s is, well, what's the clique number? Here's the clique number of this thing. So what can we actually say about this? Now, there's one argument that basically this should be very similar to this. So even though you get lots of these coupled edges, there was a sense that maybe it's actually very, very close to this. So the first result actually proved on this was the result of Conlon showing that there exists some constant c such that this is at most log squared n. So certainly you're not far off this log n, but he's losing a power here. And this is again perhaps more interesting than this, there's a result due to Van Green saying that, okay, so if gamma is Zn, and generally speaking, if I use big N, I'm going to mean so throughout. Well, I'll use big N to denote the size of the group. It will always be a function. Then in this case, omega of G is actually at most C times log. So this is actually true in this particular case, which is a result of Van Green. So underlying that is a lot of work where you're trying to count the number of subsets of Zn of a particular size for which the sum set, when you add two elements together, for which the sum set has a particular size. Done more carefully, there's actually another result of Ben Green and Rob Morris showing that you can get 2 plus little o1 times log base 2 of n in this case. So that's a result of Green and Morris. Okay, so actually this seems to really
Sorry, yeah. Probably one question, but I mean, are these all results like this high probability?
Yeah, sorry, this is you're completely right. I should have said that somewhere. So all of this is with high probability. So this is with high probability. This result here is, yeah, that's with high probability as well. But all of these are with high probability. Of course, you can choose, there's always some Cayley graph much higher. Okay. So what if you change the group? So Ben Green has some more results where he looks at this group. So Z2 is the end. It turns out here the answer actually isn't log n. So here the answer is that omega of gamma of a half is up to constants equal to log n times 20 log log. So you can end up in the situation where there's actually this extra log factor. So not only is that there in the upper band, but it's also there in the lower band. It's necessary. So the main issue is that this group contains many subspaces. And those subspaces form loops. So basically, you have a pile of subspaces inside here. In fact, there's basically too many subspaces. There's more than necessary. And just working out whether those subspaces appear or not gives you cliques, and it gives you this particular band. So you end up with this extra log factor. Okay. So the question still stands. So what is actually happening here? So we're in this situation where we know that sometimes it's log and sometimes it's log times log log. What's the general result? So the general result is theorem by myself and these authors that I mentioned, which says that, okay, so again, with high probability, for any finite group gamma, this, I'll state it actually, you can use it for a general P, with any P between 0 and 1, the sleep number of gamma P is at most some absolute constant times log n times log n. So actually, that's always true. In essence, we believe, but we can't prove that that in some sense Z2n is the worst possible situation. Similar things happen if you look at Z3n or Z5n or whatever. Similar things do happen within here, but it seems that Z2 to the n is the one with the most subspace. Okay, so I want to tell you a little bit about the proof of this, but basically it doesn't really have very much to do with the group theory setting at all. It's a more general setting, and within that more general setting, it's also true. So let me just say a little bit about that more general setting. Okay, so the general setting has, we look at what are called random entanglements. So given a colored graph, a complete graph, and with coloring C, the random entangled graph GC of P is formed. So basically the idea is, I'll write it up in a second. You have this coloring. Basically each color class gets chosen with probability P. And if you look at Cayley graph, then the Cayley graph, you basically can think of it as a color, because each edge, XY, gets color S. It gets color, the element from the Cayley group, from the group it's defined. So it is formed by taking each color class with probability. So again, if you're looking at Zn, then your Cayley graph has, this is one possible collection of edges, but you're also getting, this is also a collection of edges. Right here, but probably make this longer if I want to do this properly. But this is another collection of edges, and so on. So each of those form a color class, and all I'm saying is that each of those occurs with probability p, and you end up with some resulting graph out of this. And the theorem that generalizes that one up there says that the same result holds. Right? So if C is bounded. So what I mean by saying a color is bounded is each vertex has bounded degree. So rather, in each color, if I fix a particular color, like here, if I look at these white edges, then each vertex has degree at most 2 in those white edges. That's generally true of Cayley graphs as well. Sometimes it's 1, sometimes it's 2, but it's certainly at most 2. Then, with high probability, the omega of this GCP is at most P there, is at most some constant depending on delta and on P times log n. Okay, so the delta bounded means the degree at most is delta. Okay, and that theorem implies this theorem just because of what I said, but it's always the case that within a Cayley graph, the colorings have max degree 2. So I just apply this with 2, and it gives this. Of course.
Some people just normalization the statement of the extra log factor. If you base these results, the natural question would be, can you always tell when the extra log factor kicks in?
Yes, so we have been thinking about that, and it's to do, we don't yet have a precise answer, but we hope to have one soon, but it's largely to do with how many subgroups you have. So if you have a group that has lots of subgroups, which can happen not just for abelian groups like this, then those subgroups tend to give you cliques. So you want to avoid having small subgroups. And there is a continuum of groups going between those that are quite open, like Zn, which doesn't have, like especially if n is prime, doesn't have any small subgroups, to things like Z2 to the n, which has loads of these subgroups. Okay, so so that removes the addition for now. And actually, we can remove the probability as well. So the probability, it turns out that what this really boils down to is the following theorem. Okay, so basically, I want to say that if you have coloring, then you can't have too many subsets that contain a small number. So, in any, I'll state this for proper colorings, even though Cayley graphs have degree 2, but you can change this from proper colorings to delta bounded colorings by using some simple arguments. So in any proper coloring of Kn, the number of subsets of order n with at most Kn colors is or equals k times n colors is at most c to the power of k log n times ck to the power of for some c. Okay, I'll say a little bit about where this comes from in a little while. It's almost tight. It's not quite tight, but I'll say more about how or why it's tight in a little while. But for now, I just want to say that what it's saying is that you have Kn, it's properly colored, so each vertex, every edge coming out of it is a different color. And I want to say that the number of subsets of a particular size, which don't have many colors on it, is a small number. So this is some small number. If you know this, then there's a little bit of work that needs to be done, but essentially you can do a union bound. And you can say, well, okay, so how many subsets are there with Kn colors? Then, well, the probability that that's monochromatic will be 2 to the power of minus k. You add up over all the possible sizes, it cancels out, it gives you the required approach. I said you do need to do a little bit of work because you need to first guarantee that you have some minimum number of colors that can't go too small. But besides that, it essentially works. Okay. So I want to tell you just a little. The proof of this is actually quite simple, and I want to give you some sense. Okay, so here is a sketch of the proof. So it's actually convenient to think about sequences rather than sets. So we'd like to find the number of sequences, V1 up to Vn, of vertices with this. And with this, it's enough to prove, so enough to show that it's at most basically the same bound, c the power of k log n times, okay, so I'm going to put c or n. So this or is actually k times n, but if I'm reordering the sequences, I divide by n factorial, which is around n to the n. So just allowing for the sequence thing, this is basically the same result up to n to the power. Okay. So I want to try and find this by a kind of inductive process. And to begin with, I just pick a vertex. So let's set V1 to be an arbitrary vertex. There's obviously n choices for that, because there's big N things in total. And I'm going to set V0 to be just this vertex V1, and N0 V1. So I have a process that goes from here, and to begin with, we're going to define, so we will define V0, subset of V1, subset of V2, so on. And basically, what we're going to do is we define these sets, and we have inside this V1 up to Vn, they appear in some order, not necessarily in the order you actually see. So like V1 could have V1, and then like it'll be the 9th index and the 12th index, and it will be mapped to some specific vertex within my overarching. And we will have ni plus 1 equal to Ni plus Ui, where this Ui is the ceiling of Ni times N minus Ni over R. You'll see where all this comes from in a minute. Okay, so suppose we have Vi.
David, this process is not generating sequences.
Sorry, say again?
You are now building the process generating those sequences.
So I'm going to build up this sequence. So I have V0. I'll now build V1 and so on until it reaches everything. We build up to cover everything. So suppose we know Vi and the indices they appear. So this Vi is basically just some subset of this Kn that we started with. So it's so Vi is something here, and then there's some remainder, which is this V less Vi. Okay, so how many edges are there between this Vi and this V less Vi? So what we're going to do is basically reveal some colors, and those colors are going to create a connected component. So up to point I, I've revealed I colors, and I have some connected. Back here, when I started with just 0, there's no colors to connected components. There's just this first element. So, but here I have I colors inside here, and we formed some sort of connected component. All right. So between here and here, there are how many colors? Well, there's Ni times N minus I edges in total going between these. There's R colors in total, so the number of colors that have the same the number of edges that have the same color is at least, so there's at least ceiling of Ni times N minus Ni over R edges between Vi and its complement of the same sort. Okay, so somewhere in here, there are edges coming out of here, going across to there, which all have the same color. And because it's a proper coloring, they actually form a matching. So I'm just getting there's some collection in here of, remember this is actually UI, of UI edges, UI vertices, that map the UI vertices over here. So what I do is accept Vi plus 1 could be equal to Vi union these UI nearly matched vertices. And we grow, we continue. So we've gotten to this point. We now have our U set Vi plus 1. We look at Vi plus 1 and its complement, we do the same thing, and we keep going. The key thing is how much we got at each step. So in order to determine how many possible sets there are, we need to figure out, well, okay, so how many choices were there? And there's two things here if we're looking at sequences. There's what those vertices are, and there's also what positions they lie in within the sequence. So the total number of choices so the number of choices for the Vi plus 1 and its positions. So that's given that I already know what the positions are, what Vi is and what its positions are, is, okay, so How many colors are there? Well, it's properly colored Kn. There's at most big N squared colors. Colors. How many, so I have UI new vertices that I'm adding. How many positions can I put them in within my set? So there's n minus ni vertices in the I+1. They're the leftover ones in the sequence. And I can choose their positions this many different ways. So this is the choices for the indices. And now an interesting thing happens. So I also need to choose which vertices I'm actually choosing. So naively, a sort of first guess would be, well, it's n minus ni times ui is one way. So each one of those, I already know what the positions of the first ones are. So the number of ways of choosing these things is, well, the first one has n minus ni places it goes. You could make it n minus ni choose ui, but that's one possibility. But actually, you can also just do it as ni choose ui. And the reason for that is that, well, I can just look back here, pick one of these vertices out of here, and the unique thing matched to it is the vertex over here. So I can actually do my job of just picking the vertices in here, and it will give me what I'm looking for over there. So I can do it that way. So you can sort of positions of the vertices using the match. Okay. All right, so we're almost done. Actually, if you basically multiply up what happens for each step, then this is essentially it. But how many steps are there is another thing that we use. So how many steps? Well, okay, ni plus 1 is equal to this ni plus ui. That's roughly ni times 1 plus n minus ni over this, or this is around k times n, this is around n, so this is around ni times 1 plus 1 over k. So the number of steps is we're done in some constant times k log n steps. Okay, so multiplying all this up, this ck log n is just this big N, the power of this ck log n. This stuff here, if you cancel it outright, I'm not going to do it, but if you cancel it outright, it gives just this ck to the end. So you get everything. Okay.
So sorry, I'm trying to follow you here, but like you started with like this set V is this set of P1 up to Vn of this of these vertices that you want to that, right?
Yeah. So it's in a specific sequence is one of the important things. So
okay. So you are so you are counting those, and then there are those UI edges between Vi and V minus V.
Yeah.
Where do you get the UI newly matched vertices?
So you picked this specific color, the specific color that has lots of. So you have this matching. Now you have that specific matching in that specific color, so you know where the matching is.
Why is that?
Because I've said at the start, so I said this is a proper color. So the assumption of the theorem is that it's a proper color. So each color class has to actually be a match. Yeah, so that's what I meant by proper coloring here, is basically that every family or every color class is like this. So that's slightly different to a K graph where you're allowed degree 2, but it's easy to lift this to the same theorem basically about basically you can use Vising to recolor to make it a proper coloring, and in doing so you gain at most twice the number of colors. Okay, so so the main idea of this proof. And that is enough to actually do this clique number. But for other applications, you need more, and you need something that's a little bit tighter. And it turns out that basically the tight version of this, same theorem, is basically the same thing, except, sorry, I wrote this wrong. It should have been the actual statement more or less. No, this is the correct statement. So this n that you're getting to the ck log n is this same n, but each choice, at each step you have n squared colors, and it's this power to the ck log n. But basically this is the wrong dependency, and the correct dependency is this. So where it's not k times log n, it's actually k plus log n. I'm not going to go into this. This is much harder to prove than what I've just talked about. You have to do a lot of work where you're chasing. Here you're sort of roughly chasing how components grow. And if you follow your nose, you can see how the components grow. For this, you can also follow how the components grow, but what you need to prove is essentially that as the components grow, each color class or each component has lots of new colors coming out, which means that as you choose the next color, it will cause components to coalesce. So you're looking at components growing and coalescing. But if you do that very carefully, then you can get this result. Why is this tight? So all right, so one thing is that if you look at subspaces, so the number of d-dimensional subspaces of F2D is roughly so it's basically 2 to the nd minus d squared, but let's think of that as being roughly 2 to the nd. Okay, so so if you think of I keep writing this wrong, this should be little n. Okay, so what's happening here? This is basically n to the d. And what is d? Well, if your set has size, so if 2 to the d equals n, then actually d is equal to log base 2 of it. So you're getting n to the power of log base 2 of n subspaces of size n. Now, I said each of those are cliques. So basically that gives you this n to the log n type behavior. In fact, it gives you this n to the log n type behavior, but this c should be 1. And if you can improve that to 1, it would be a very nice result that I might come back to, but so you definitely need this factor. You also need a factor so actually, I guess what you really should have is that if d 2 to the d is equal to k, because really within the subspace, that's the number of colors you're actually getting, then we're getting n to the power of log base 2k. And within that set of size kn, the number of ways of choosing a subspace, a subset of size n, is kn choose n, which is around k. So that actually gives you this second factor here as well. What about, there's still a factor missing here. There's like this n to the k factor. Well, that comes from if gamma is an abelian group with subgroup of order n minus k, we can choose any k additional elements and get that a plus a is at most k times. So basically, you have this thing of size n minus k. Every new additional element just gives you an extra coset. So you're getting k times n in total, and the number of ways of choosing those k additional elements. So the number of choices for this is at most n power k. So that's this factor. So all the factors are necessary. Whether the constants are necessary is less clear. Okay, but I said that we actually need this much sharper version for something. So what exactly is it that we need this much sharper version for? So it's another conjecture of Noga-Alon. So actually, here's a conjecture of Alon, and it says the following. So there is an absolute constant C such that every finite group has a coloring, has a Cayley graph with no clique or independent set. Set of order C log. This might even be true with 2, but instead of C. But basically, he's saying that, okay, so maybe it's the case that there is some Cayley graph that you can choose such that that Cayley graph is what's called C-Ramsey. So this whole thing is what's called C-Ramseyness. And it basically says that there's no clique or independent set. So Ramsey's theorem tells you that you always contain cliques or independent sets of size log base 2 of n. What this is saying is that you can also find constructions coming from any Cayley graph that gives you things that are very, very close to optimal. So that's the okay. So in some sense, we know that this conjecture needs some ideas because you could just try and take a random Cayley graph. But we've already seen that there are cases where log n times log n is necessary. So you need to do something clever if you want to find a Cayley graph for which, like over Z2 to the n, for example, if you want to find a Cayley graph for which this works. Turns out we can't do Z2 to the n, so it's still open. Well, open case. Good problem to think about if you're interested in this. So Z2 to the n is open, and Z3 to the n is also. But we can do Z5. You'll see why in a second.
Using both imply that instead of C log n, you can put
Yeah, exactly. So everything we do, if it works for cliques, it also works for sets because it is complementary. So yeah, we can get log n times log n, but what about this? So there exists in fact, we can do something slightly stronger here, a self-complementary, by which I mean there's an automorphism from something before. So for almost nothing we've done before, apart from everything I've stated already, which was this Zn stuff. That was the only thing that's actually happened. So there exists a self-complementary Cayley graph, C Ramsey, Cayley graph over F5.
So complementary means isomorphic with its.
Isomorphic to its complement. Yeah, so there exists, there basically exists some sort of automorphism that takes the clique to itself and maps all edges to non-reducing parts. In fact, that actually solves a conjecture of Allen and Orlitsky. So they had a paper on communication theory in the early 90s, where they asked, is it the case that there exist self-complementary C-Ramsey graphs? So, and this already solves that as well. By the way, if you try and Google, this is very annoying because Orlitsky's first name is Allen. So, okay, so I want to give you the sketch of this. This is why I said without much addition, you actually do need the addition part here to define this. Okay, and again, this is more of a sketch than an actual proof. So, so let's split Z5 to the n into cyclic subgroups of the form 0x, 2x, 3x, 4. So you have these, the whole thing can obviously be partitioned into such a thing. If you're missing an element, then just choose an element that's not in it and do this, and it will give you the next cyclic subgroup. So, okay, so what I'm going to do is I'm going to sort of forget about the 0, and then I'm going to partition the rest into 2 pieces, and I'm going to choose one of those pieces at random. So let's form a random S by using either x2x, sorry, x4x, or x 2x 3x to be n. This is self-complementary because x and 4x are minuses of each other. 2x and 3x are minuses of each other. And the map, so phi x goes from x to 2x, takes edges to non-edges. So rather than taking a random thing, we're pairing them up in a sort of very neat way, and we're saying, okay, so we either get x4x in our set, or we get 2x, 3x. We don't get both. So if this is in our set, this is not, and vice versa. So you can also think of this as a red-blue coloring. This gets red, this gets blue. And it gives a self-complementary thing. What do I want to say? So maybe I won't say too much about the proof. You need some ideas. So you need both this theorem, theorem I deleted here with the correct count. You need that thing with the correct count, and you need some little bit of work in additive combinatorics to push this through. But basically, the key idea at the bottom of it is that this is the actual coloring we use. If you're interested, you can ask me at the end. All right, so what else can we prove in this kind of direction? So okay, so like I said, this Z5 to the n thing it really depends on the fact that we can peel off, that we can split into this x4x and this 2x3x. That's not possible here. So when you were asking about z2 to the n, z3 to the n, here if you split this into cyclic subspaces, you get 0x2x. X and 2x have to be together because they're minuses of each other. So there's no way to sort of split red and blue apart. Here it's even worse. There's just one, right? But the problems seem similar. There must be some way around it, but we haven't been able to see it. Like, it would be really strange, I think, if Alan's conjecture wasn't true for these, but we really don't know how to take them. However, we can prove several other results. So the same holds. For p to the n, any p congruent to 1 multiple. So in order to do this splitting in the right way, exactly the same proof essentially works for this z p. But then we can actually lift the result. So in fact, the same holds for any abelian group of order coprime to 6. You really don't want 2 dividing it somehow, or 3 dividing it. It causes trouble because, you know, not only do you have f2 to the n, but f4 to z4 to the n causes trouble and so on. However, once you have this, there is a way to lift it. So the same holds actually for abelian groups of almost all orders. And that's enough to actually, so we do know that basically for almost all orders of sizes of groups, this conjecture is true. But again, this is only for abelian groups. For non-abelian groups, we don't really know that much. We know a little bit, but not so much. But everything we know essentially says that the group has to contain a large abelian subgroup. Okay. So what else can we do? I'm just going to finish by talking about one other theorem that we have. But first, let me recall Feynman's theorem, which is a big theorem in algebra combinatorics. So one version of Feynman's theorem is the following. So if A is contained in z2 to the n, then and A plus A is at most k times A, then there's some subset A prime. There is A prime, a subset of A, which is large. This is some constant depending on k, and that A prime is itself contained in a subspace. A prime is contained in a subspace of order ck. You sort of see we've gone from, we started with a subset A, we've passed to a subspace, passed to a subset, and then it turns out that A prime is contained within a subset. So we've sort of gone down and back up again. Basically, you contain, if you have small subset, there's a structure theorem saying that there's a small subset, or sorry, a large subset that's contained in a small subspace. This is very important. Like I said, there was a major advance recently, so breakthrough by several people. So Gowers, Green, Manners, and Tao. And basically the result says that you can take this constant to be polynomial. And this is something called the polynomial Feynman-Rüge conjecture. And it is very well one of the main open problems in this area. So let me state one of our other theorems. So here's a theorem. Again, this is myself, Jacob Fox, Roy Fahn, and Liana Euphemian. And the theorem states that, again, the setup is in any Kn with a Kn with at most Kn colors, there is a subset of order n/2 with a spanning tree using a small number of things. Some constant k plus log n colors. So you
Now the colors are on the
yes.
limit.
So the colors are on. Sorry, so this should be a proper coloring as well. So the properly colored.
But it's,
Sorry, let me just check. I'm getting confused between the two different settings, I think. Yeah, so every proper coloring with at most Kn colors is right. There's a subset of order n/2 with at least, with at most that many colors. Okay, so basically you can find a tree that doesn't use very many colors. So what was your question again?
I was just thinking, what do we color the
Oh, so you're coloring the edges. Yeah. Okay, so what does this have to do with anything? So it turns out you can apply this to this setting over here. So maybe I should have used little n up there, but anyway, let's suppose we have a set A of size n with A plus A at most k. So what I can do is I can look at the graph whose vertex set is A, and I can look at what happens for if x and y are joined, they get color x plus y. Okay, so by this theorem, there exists some A prime greater than or equal to n/2 with at most ck plus log n colors on a spanning tree. But if you take just some vertex of this tree and you take all of these colors, so taking some v in A prime and all of these colors, you get a subspace with at most subspace with at most 2 to the power of ck plus log n plus 1, which is 2 to the ck plus 1 times n points. So actually, this theorem actually, and it's completely abstract, completely just about what you find, what sort of spanning trees you can find in the subspace, implies Feynman's theorem. So really, Feynman's theorem over z2 to the n is really just a graph theory statement. Now, this doesn't give optimal bounds, because what we get here is something polynomial in ck, but here you're exponentiating that in the proof, so you end up with 2 to the power. Okay. So there's more I can talk about, but I think I'm basically out of time. But let me just again flag that this question that's open here about
It's like when you do it, like 5 sentences. So it's,
how do you prove this?
yes.
There isn't really a 5-sentence proof. It's also again to do with the growth of components. So you do it randomly. You expose colors at random. You see what sort of components that they actually generate. But essentially, the instinct is that, okay, so I generate a pile of components. I've exposed up to this point I colors. And when I expose my I plus first color, what I guarantee as I go along is there's lots of colors going between these. They're sort of fairly multicolored. So when I expose a new random coloring, at the very least, I expect that I will pair up 2 of these. In fact, I generically sort of expect that I'll pair up some bunches of these, so the components will double in size. And if they double in size, that's good, because in log n steps, you'll hit n. So the instinct is this, that I'm getting these components that are coalescing with it. Okay, so like I said, the open thing is to do this thing here, even without this self-complementary, over Z2 to the n, or Z3 to the n. So if you have a clever idea about this, I would love to hear it, because we sort of run out of ideas now. Okay, thank you.